Okay, so this is 11.4 continued. So let's do an example. It says find a unit vector that is orthogonal to both u and v. And we're given our u vector and v vector here. So to be orthogonal means it's perpendicular to both these vectors. So to find this vector, we're going to find the cross product of these two first. So let's do that. Okay, so I've written my cross product definition, so let's start doing it here. So we'll do the I component first. So cover the I column. So it's going to be then 2 times minus 2, so it'll be minus 2. And minus 1 times 0, so minus 0. That'll be I direction. Then we'll do the J column next. That'll be minus. It'll be 1 times minus 1, so it'll be minus 1 there. And it'll be minus 1 times 4. Minus that, so it'll be minus 4 J, and then the K one would be 1 times 0, so it'd be 0. Minus 2 times 4, so minus 8. Okay, and simplifying this, we get, negative 2i minus 3j minus 8k. So this vector, this cross product should be orthogonal to both of those. We can check it to make sure we did it right. So if we dot it with u and v, it should be 0. So let's just check that. So let's check that here. So u dotted with u cross v. My u is up here, so it's going to be 1 times minus 2. So it'll be minus 2 there. It's going to be 2 times minus 3, so minus 6 here. And it's going to be negative 8 times, negative 1 times minus 8, so it'll be plus 8. So 0 there, so that's checks. And also v dotted with u cross v should be 0 also. Let's check that. So dotting here, it'll be 4 times minus 2, so it'll be minus 8. That'll be 0 times minus 3, so it'll be 0. That'll be negative 1 times minus 8, so it'll be plus 8. So that's 0 also. Okay, good. So we've shown it's orthogonal. And it says find a unit vector, so we need to normalize our u cross v then. So here's how we normalize it. So we need to divide by the magnitude. So take your u cross v divided by magnitude, that will change it to a unit vector. So let's find the magnitude of u cross v now. So the magnitude of u cross v, well, u cross v is here. So the magnitude would be the first component squared, so it'll be minus 2 squared, plus the second component squared, so minus 3 squared, plus third component squared, so minus 8 squared. So adding those, you get square root of 77. So then up here we can write that. So replace it up here. And now what I'm going to do is I can pull the square root of 77 out in front of the u cross v. And I'm also going to pull a minus sign out from my u cross v, so let me write it here. So pulling out the minus from the vector up here and the square root of 77. So my unit vector could be written this way. So you can check if you took the magnitude of this vector, it would be 1. Okay, so we're done with this example. Okay, now we're going to go on to another theorem now, Theorem 5. So let me state that. I'm going to write some things here. So Theorem 5 says the volume of the parallelepiped determined by the vectors u, v, and w is given by absolute value of u dot v cross w. I've drawn my 3 vectors here. So these 3 vectors will determine a box. It's called a parallelepiped. So let me draw it in here. Okay, so the box would look like that. This angle here isn't necessarily 90 degrees in there, so it's like a slanted box. Okay, I'm going to call the area down here B of the base. Let me do that. So letting B to be the area of the base. I'm drawing it over here also. Now I want to try and figure out the area of this guy here, so I'm going to cut it up. So let me draw in some dotted lines. Okay, so I drew a dotted line here. So if I cut this right here, this little triangle, and lifted it out, it would fit here exactly. So pretty much the area of B, so B would be the height times the magnitude of V. Let's figure out the height here. So it's going to be the opposite side. So we're going to be using sine to figure it out here. So I'll have sine of theta equals opposite over hypotenuse. The opposite side is h. Hypotenuse is w, well actually magnitude of w. We can then solve this guy for h. Let's do that. So multiplying both sides by magnitude of w, we get h equals magnitude of w times sine theta. Okay, so now we can find the area B. It's basically going to be h times magnitude of v. So let me write that down here. So we get then B equals h times magnitude of v, but h is magnitude of w times sine theta, so it's basically going to be magnitude w, magnitude of v times sine of the angle between the vectors. And from Theorem 4 then we can write this as v cross w, so let me write that here. So using Theorem 4, we showed in Theorem 4 that this guy here equals magnitude of v cross w. Okay, so let's keep going. Okay, so now I'm going to make some cuts in my parallelepiped now, so let me do that. Okay, I've drawn a few things here. The first thing to note is v cross w, which I've written here, will produce a vector that's perpendicular to both v and w, so it's going to be pointing up this way. So it'll be 90 degrees between this vector and w and v. And then if I made some cuts here along the dotted lines, so I want to make the dotted line here perpendicular to the B plane down here, so perpendicular to V and W, and cutting it this way. This piece would fit in the back over here, so you're straightening the corners here, making it 90 degrees. And I'm calling phi the angle between U and the cross product V cross W. So the volume of the parallelepiped then would be h times b. So let's find h here first. Or maybe I'll call it h1 since I already used h over here. I call it h1 here. So let's find h1. So notice h1 relative to this angle, it's on the adjacent side. So notice here. So we'll have then the cosine of phi is adjacent over hypotenuse. The adjacent is h1. The hypotenuse is magnitude of u. So we can solve for h1 by multiplying both sides by magnitude of u. Let's do that. Doing that, we get then h1 equals this. So then the volume of the parallelepiped will be then h1 times the area base. Area base is this. Well, actually, yeah, sure, right like that. Okay, so let's do that. So we have our volume n equals h1 times b. Using this for h1 up here, the magnitude of u, and b is equal to magnitude of v cross w times cosine of phi. Okay, that's the volume of the parallelepiped. We still need to show it's equal to this guy here. So let's say recall something here. I'm going to erase right here, right now. Let me do that. So now I'm going to use Theorem 2. It says the cosine of phi equals the dot product of the two vectors divided by magnitude multiplied together of the two vectors. So our phi angles here is the angle between the v cross w and u in our picture over here. So therefore cosine of phi would be v cross w dot u divided by magnitude of v cross w, magnitude of v. I can then multiply both sides by this. Let's do that. Sorry, just notice there should be a u here, not a v. Right here. Okay, multiplying both sides by this. Let's do that. So doing that, we get magnitude V cross W, magnitude U times cosine of the phi angle equals V cross W dot U. But notice this right here is equal to this over here. So therefore this can go in place of this right here. So we can conclude then, so pretty much we're done now. So making that substitution we get, so substituting, we get the volume then of the parallelepiped is, I'm just switching the order of those around the dot product, U dot V cross W, and that's what we're trying to show. I guess up here it does have an absolute value, and that's fine because when I drew the picture, you can see from the picture here, I'm assuming the angle is in the first quadrant. If the angle was in the second quadrant, then you'd need an absolute value. Okay, so don't worry about that. So we've proven a result then. So claim follows. So we're done with theorem 5. Okay, so we're actually now done with 11.4. So I'm going to leave it there in this video. So we'll pick up in the next video at 11.5. Okay, so let's leave it there.